Hi, everyone. Welcome to Foresight's Neurotech Group. I'm really excited to have Tom Burns with us today. And Tom, you'll be discussing at the interface of AI safety and neuroscience. And we're really excited to have you here. I'll share a lot more info about you in the chat, but for now, please take it away. The stage is yours.
Great. Thank you so much. Very happy to be here. My talk title, as you just said, is at the interface of AI safety and neuroscience. If you want to follow up with me personally, you can check my Twitter, or now called X, TF Bands. All right. So just to introduce a little bit of my background, since this kind of is an interdisciplinary talk, I wanted just to highlight that I come from a background of neuroscience and ethics, and more recently AI, and I had the pleasure of being involved in different organizations like those on the right. And at the moment, I am a postdoc at Cornell University, and they have a new AI center. I think many of you will know that large language models exhibit biases and misinformation. So on the left is an example of ChatGPT showing bias towards certain political parties in Germany. Now, we might have our own biases politically or wishes politically, but I would contend that we'd prefer these systems, these AI systems, to be more neutral. On the right are some examples of hallucinations of harassment scandals, sexual harassment scandals, or corruption scandals. And of course, people have different issues with that, naturally. What's more, not only are these sorts of problems existing today, there are some future ones which we don't yet know exactly how to grapple with. So suppose that we had an AI system which does a very complicated sequence of things or witnesses a very complicated sequence of things. In this case, things which relate to the safety of a diamond in a room. And this system is designed to keep that diamond exactly where it is safely. Because these actions are so many and so complicated, we say that we don't understand how it works, but we do see the predicted output from the system. In this case, the diamond is still there in the first two examples, but not there in the third one. And so we would say, okay, the first two examples are good, and the third one is not so good. But this may not reflect reality. This second example could be that someone's erected a screen in front of our camera that's observing the room, and actually some robber is either in cahoots with the AI or is fooling the AI in some way. And that sequence of actions on the left actually caused this outcome on the right. And in order then for us to distinguish between the first and the second case, that is on the top and in the middle, we need to understand the actions and the predictions more carefully and more fully. If you look at AI and academia and industry, you see that there's really no slowing down either. There's an increasing number of papers every year, and people like Sam Altman have announced that, or it's been reported that they are seeking a lot of money to develop AI further, and particular AI hardware. So I want to pose a case to you for neuroscience-inspired or led interpretability of large language models and transformers more generally. So I hope I've already demonstrated to you this first premise, that there are problems with current LLMs today, and also too that there will be future problems that really, if these systems remain inscrutable, we're going to have a lot of difficulty to align them with our own judgments. And an assumption for now, but which I hope you will agree with me later is more of a premise, is that we can use neuroscience to help. And I like to say that, neuroscientists were the first interpretability researchers in this modern lingo. No, they are trained to study neural networks, and they can help us understand artificial neural networks. And the conclusion is here that, well, we can help mitigate harms and deception and increase the opportunities for good results as well, using interpretability-led research, neuroscience-led interpretability research. And so this talk is broken into two parts. The first is I'll talk about building bridges from neuroscience to AI. And in the second, I'll talk about building bridges from AI to neuroscience. So let me go into the first part, which is neuroscience to AI. On the right, you can see a 3D model of a human skull, and the red shaded volumes are the hippocampal formations of the left and right hemispheres. And these areas, as well as some adjacent areas called the entorhinal cortex or cortices, are responsible very heavily for memory and navigation. And the classic example that won the first Nobel Prize in this particular area of research was that of place cells. And in this case, you have a rodent that runs along, for example, a linear track, but it could be 2D or 3D, or you could use virtual reality to create extra dimensions. And the example in this is that different colors represent different neurons, different cells, which are in the hippocampus. And those different dots are different activations or firings of those place cells. And you can see that they're grouped such that they cover particular regions, but slightly overlapping regions of this track in a continuous fashion. So there is a theory called associative memory, which is like a theory or framework which attempts to model the hippocampus and this kind of activity. And what it does is it uses a certain number of random patterns. These could be places, for example, or they could be memory items more arbitrarily. And we assign these as vectors with plus minus 1 over n neurons. And then we say the state of the system is given by the vector sigma. And we update sigma, we update the states by looking at all the other neurons which are connected to our neuron. And in this case, they're all connected typically. And then we weight their activities by Wij. Wij is basically saying, following Hepp's rule, that if we fire together, then we wire together. So in that previous slide, you saw some of the overlap between the spiking activity regions of different neurons, different place cells. And in that case, they're firing together, they're active together, so they wire together, they form an association. And this causes, if we think in the physics sense, there to be an energy landscape, which all these equations can be derived from. And in this case, we can have a problem though. So what the energy landscape sort of implies, if you don't really follow the equations, is that if we start at some point, on the x-axis is the different values of sigma, the different states of the network, and on the y-axis is the energy, E. And if we started at this state, then we would fall down the energy landscape and go all the way down here. Now, ideally, these wells in the energy landscape, or these deep valleys, would correspond exactly to these different memory items, Xi1 and Xi2. But in this case, they don't, because they're close together and they're sort of fusing together in this energy landscape. However, if we adjust this energy function and have a function f, which is operating on this term, and if we make that function something like x to the n, then the implication is that we're creating many different summons of groups of different neurons, and therefore we're having higher order interactions between the neurons. And when we do this, the energy landscape separates such that we can distinguish these two memory items. Now, in the limit, this f of x could be e to the x, right? That's an exponential number of interactions between the neurons. And if you do that, these equations are what follows in terms of your update for the binary case. And then if you go to a continuous value for the neurons, instead of just plus and minus 1, you can have any number, any real number. Then you finally get an equation here at the bottom, which includes something called the softmax. The softmax looks like this, takes a vector and gives a vector, which basically operates by normalizing such that the sum is 1. And it highlights the top value or the top nth values such that they are more highly weighted. And for those that know about the attention mechanism and transformers, such as those behind ChatGPT and others, you'll know that this equation here is almost exactly the attention mechanism, except for the fact that this capital Xi, well, some of the variables are different, but also this capital Xi it's the same as this, and it should be something different in the case of the attention mechanism. And I'll get back to that in just a few slides. Now, as I mentioned, this limit case implies an exponential interaction between the neurons. If you want to see a more realistic finite case, you can see a paper that I did with Tomoki Fukai last year. And again, this creates a situation where this model of associative memory, which started back and still is connected to the hippocampal formation, it is akin to the attention mechanism of transformers. Now, I mentioned that capital I is both inside the brackets and outside. The consequence of that is that what we're performing in this operation is auto-association. That is, given partial information about some memory pattern, we are recalling the full memory pattern. We're going down that energy landscape to retrieve the full memory pattern when we're close to it. However, there is something which is equally valid to think about, which is heteroassociation. So that is, if I recall one memory, I direct myself to a different memory relating to that memory. So, for example, Homer's wife is Marge. That would be an example of heteroassociation. Now, this has been studied in associative memory quite extensively, but almost always they take the following form, where essentially it creates a topology of memories which forms a ring. If you identify in this equation, the index for p+1 is equal to 1. And so in that case, you just move around. You have a long line of these different memories. They're associated each to each other along the line, and then they finally link up at the end. Now, there is a different way to do that same kind of thing, which uses fast and delayed synapses, but again, it has the same sort of topology in terms of the memory. So what I've done is created a model which links these auto and heteroassociative components together in this following model. So we can have a population state vector, sigma, and we control the dynamics using these two variables. It's not too important what these are. Let's say constant throughout the simulation. And same here, this is just a normalization term. And then importantly, capital Xi here is again the memory bank that we have, the different memory items. But I just get my laser pointer. Importantly, this Q has been replaced from what was a Xi. So it was a Xi out here, and now we've replaced it with a unique matrix Q, which we identify as a mixture of autoassociation and heteroassociation. This heteroassociation comes through capital M, A and H are the auto and heteroassociation strengths, and M is the normalized adjacency matrix for memory graph, curly M, on P memory vertices. And you just saw an example of curly M in the past, and in the slide just before, it was a circle in that case, but where each of those vertices represented different memory patterns. But in this model, we could have any graph. And here's an example again of the circle, but now using different values of A and H. So in just a small reminder, A is auto-association strength and H is heteroassociation strength. And in this case, each row is showing a different time step over 101 time steps. And what you can see is that we begin by stimulating one particular pattern. And in this case, where we only have auto-association, we retrieve still that same pattern. But now, if we add some heteroassociation in the second column, we, at the end, broaden our activity range so that we cover a few of the adjacent memory patterns. And then if we now have a negative A and positive H, we broaden this even further. However, there is a possibility that if you have too much negative auto-association, that you'll just have this neutral quiescence state. So these are the 4 different modes that this kind of model can operate under in general. And this allows us to do a few different things. So first of all, we can look at multi-scale graph representations. So here's something called the TUP graph down below. What you can see is starting at the auto-associative regime where we just stay on one memory pattern and end on one memory pattern, up to the right, where we start on the same memory pattern, but now we heteroassociate more and more, we actually can do something like clustering and at different scales. In this example, we have sequence recall or error detection or correction. And in this case, each memory pattern is a frame of this video, or more specifically, a sparsely sampled frame. And what we're looking for is sort of a neat diagonal line that would represent moving forward in the frame sequence or backwards. It's the same thing. And not getting stuck. Like in this first example here, we're getting stuck on the same few frames and just repeating over and over and over, because there are many correlations between the different frames, so they're very self-similar, and therefore we get stuck. However, at a certain range of A and H, a certain choice of A and H, we actually get proper recall of the sequence. So we don't get stuck anywhere and we don't skip ahead. And this is also shown using the cross correlation between the frames or the memory patterns under this dynamic regime. You see that it's a clearer diagonal in this case. Another thing that this model can do is simulate finite automata. So this is an example showing text and video, images rather. So you can see here these different natural language strings, which are embedded in the memory patterns using glove embeddings. And then these images are just pixels, and the memory patterns are unions of these. And what you do is you can then simulate by giving some sort of text and then looking up the embedding, putting that onto the neurons, and then the states change such that they represent new character in visual form. So in particular, if you have this finite automata where you have all these four characters, these transitions between the characters, then for each transition, you have a purely heteroassociative sort of state, which points to the relevant character. And then each character has an auto-association, they there. But then when you give more information, for example, daughter from Marge or from Homer, then you go to Lisa. And what that looks like is, for example, Homer/daughter, H-D, that's the state that you end up at, and it points you to Lisa. In addition to these, we have some improved performance in terms of memory recall or auto-association. I don't have time to explain exactly how this works, but it turns out that if you have more heteroassociation in a particular, albeit non-traditional version of auto-association, you can actually do better than the regular model of just pure auto-association, which is with H equals 0 and A equals 1. You can also do simulations which very closely match neuroscience data from here, the example of the temporal cortex. Now, in total, this leads to the following hypothesis, which is that transformer-based models like ChatGPT are actually stacked auto and heteroassociative models like that I just described. And additionally, that superposition, which has recently been popularized by researchers at Anthropic and elsewhere in transformers or other models, is not really something to do with like routing between circuits, but rather context switching and a type of data-dependent geometry. And so neuroscientists know quite a bit about this. And in summary, for this first part, I just want to reiterate that this is a model which more closely resembles transformers than previously, even though the equations were already quite close. In addition, we find that graphs provide quite a variety of different computations. You can do sequencing, with sequencers and clusters and simulate finite state machines, as I showed here. And this ultimately gives us some further ideas about how to interpret transformers. And if you're interested in details, you can look at the preprint on arXiv. So I'll just now go into the second part, which is going from AI to neuroscience. And I hope that we can have a great discussion at the end about all of this. And let me just quickly say something about statistical learning theory, which is what I'll be talking about, has relevance to neuroscience. So consider two vector spaces, X and Y, X being the inputs, Y being the outputs, and Z or Z is the product space of X and Y. And SLT, statistical learning theory, says that there exists unknown probability distributions over this product space. And as is typical in machine learning context, or AI context, we want to find a function that goes from X to Y. And the space of these functions is the hypothesis space. And in order to find a good function, we need to measure how close it is from the ground truth function and the reality of our function that we have in our hand at the moment. And this is the target function that we're trying to find. And empirically, because these probability distributions are unknown, we use empirical risk minimization. And in particular, this process of minimizing the empirical risk, can be considered that the learning process. And what's immediately clear is that this F sub S can be non-unique, right? And then this leads to something called degeneracy. So degeneracy is the idea that, well, there can be multiple of these functions which perform the same with respect to the empirical loss or the empirical risk. And so the situation on the left here, where we think of there being like a unique function which goes well from X to Y, is quite mistaken. And it's more realistic to think of case on the right, where there could be valleys of minima and its bottom. And more generally, you could think of these valleys as intersecting different ways. And if you want to think about it even more simply, in a geometric sense, you can just look at the minimal set and what they look like. For example, sections, these different minima. And relatedly, this can also mean that probabilities can be locally non-Gaussian. So because this input or this map between input and output is not one-to-one, then you can have these non-Gaussian local qualities. And then this is also kind of related to degeneracy in some sense. And then, by consequence, you can have very strange geometry. Now, if you're interested in algebraic geometry, you'll be interested to know that there's an algebraic extension of SLT called singular learning theory. And in this, you consider these sets as algebraic varieties. If you'd like to know more about this, I highly recommend this blog post by Jessica Flint. Now, where might SLT arise in neuroscience? Well, in a few ways. So first of all, when we have sensory information, we typically say that it's a population of neurons, not individual neurons, not precise individual neurons that are making the sensation become active, but rather some collection of neurons. And when that happens, we can say that there's multiple different sets of population activities, different vectors, if you want to think about it mathematically, which would lead to the same perceptual image in the visual space or auditory space or whatever. Likewise, even if you just had two neurons, one representing the decision to go left and one's representing the decision to go right, and these were encoding how likely or confidence in going left or right, then these activities, like if we just look at the balance of those or take the maximum, then there are a huge number of combinations which can lead to the same sort of decision making and therefore have degeneracy also. Likewise, too, in motor control, there are many different ways to grasp an object or to manipulate an object or to have a gate, for example. And so in this case, we have a manifold of possible movements which achieve the same thing. Also, too, you can think of different puzzles or different cognitive tasks that you might perform, which actually leads to the same outcome. Another example is like those prior examples are more about inference. This is more an example of internal representation and learning. And this is an example of representational drift. So in the hippocampus, there's many different cells, and people say that these cells, for example, some of them represent places. And in this case, we've ordered the cells on this first day of activity according to where they lie on the track. And over 20 days, we look again at the activity of these same cells. Now, it turns out these are quite unstable, in terms of their identities, but the underlying structure is maintained. So if we look 10 days later with the cells ordered by the first day, there's some shadow of that structure there, that diagonal line, but it's actually missing. But if we resort the cells, then we do find the structure is still there. And likewise, 10 days later again. And I contend that these could be forming different points on some minimal set, and therefore, really, it's the same sort of structure which is being maintained from an SLT perspective. And this process of empirical risk minimization has got, in this case, something to do with homeostasis. Now, in general, I quite liked this endeavor or this idea of going from SLT in particular to neuroscience, because to me, it harkens back to an ongoing sort of discussion in neuroscience, particularly of hippocampus, which is going from the left side of this slide to the right. That is, there've been now 2 Nobel Prizes awarded for place cells and grid cells. And there are many specialized cells basically in this area where they represent places or particular head angles and so on. And we think there are some people who think that this combination of cells, these specialized cells, is what helps us decode where we are and where we're going and so on. However, there's an emerging view that, or a more integrated view, which says that, well, these specialized cells don't exist in a vacuum. They coordinate, cooperate, are embodied, and ultimately lead to a sequence of actions or a sequence of sensations. And together with behavior, they are rewarded or punished or overrepresented or underrepresented. And also they have common or redundant bases. So, you happen to do most of your things in almost a 2D plane, right? Where you navigate around a city, for example, but you also have the vertical dimension. Okay. So, these 3 spatial dimensions plus things like conspecifics, that is like common members of your species and various other things form these common bases. And then those are what you're latching onto. And then those are therefore represented by specialized cells of different form. And then the way that wraps in SLT is because those different forms and those different learning processes to learn those things are also essentially redundancies of sorts, and they're essentially types of degeneracy. So the summary for this second part is that, SLT exists. It's used particularly by some researchers in a fairly new AI safety organization called Timaeus, which you may have heard of. And it offers ways to understand symmetries and learning and learning itself. And it offers us an opportunity to bring some of those ideas into neuroscience and connect it to that so that we can bring back neuroscience to help with AI safe. And there's some various other points here, which you could perhaps read your own time. And I just want to conclude with these fairly simple points. And that is that I hope I've convinced you that there's current and future risks posed by AI, that neuroscientists can help mitigate these risks and also maximize the opportunities, and that there's further work to be done in bridge building between these fields. And I hope to identify and leverage some of that shared knowledge with you in the discussion, but also in my future work. So thank you very much for your time, and stop here for the discussion. Sorry, I can't, sorry to interrupt you, Alison, but I couldn't hear you at the moment.
Yeah, I also can't hear you, Alison.
Is this better?
Yeah.
Okay. Well, then we'll just leave it at that.
Okay.
I'm testing out your mic right now. But, I have a bunch of questions, but we also have a bunch of questions in the chat. And so I first wanted to ask Zan, if you want to unmute, now is a great time. And then if anyone else has a question, feel free to just raise your hand, or feel free to put it in the chat. If you cannot ask it yourself, then I will read it out to you. Okay, Zan, do you want to go ahead? Otherwise, I'll read out you. Yeah, great. Cool. There you go.
Thank you so much for this talk. I'm very, very interested in these problems, and especially on the problem of the hippocampus and a lot of the modeling that you're doing. So it's actually the first talk I've heard that sort of tackled these issues here, and in general too. I guess the question I have is, in the beginning, you were talking about tackling the problem of bias and transformer in autoregressive large language transformers. My question with that is, I know there is a lot of theories of cognitive science, put forth around active inference, that states that an agent, in order to create a generative model, must create some sort of bias towards the world, because that's essentially what a Bayesian assumption is. These are the priors. So I was wondering, how would that issue be resolved through further understanding of how that memory is formed, if the fundamental issue at stake is what perspective are we going to take on the set of data?
Right. Yeah. So perhaps it ties neatly into one of those final slides that I was mentioning about the redundant bases of spatial or general cognition. In that case, if that hypothesis is true, then we should try to, and it should be possible to identify what the memories are in the transformed large language model, in the associative memory sense. And that isn't to say necessarily that what they do is actually memorization, but rather they do have some common redundant bases that they use, which are sort of like priors. And then in the active inference context that you were just mentioning. And then on that basis, if we identify those, then we might be able to identify latent bias that we want to manipulate or remove in some way to suit our values. I don't know if I could, I could say many things, and I suppose everyone would have many things to say about their particular values on how those sorts of biases should be treated, whether they should be neutralized or whether or not we should be inserting our own biases. But if you want to neutralize something, then that's also inserting a value that it should be neutral, right? So this is a deep conversation for maybe a different setting. But yeah, so in general though, yeah, this can be integrated into the associative memory context and I think studied.
Yeah. There's this, I remember from my philosophy class, this kind of like end kind of sigh of like, oh damn, is ethics just kind of like the continued renegotiation between which biases we call values and which we call biases? And we've made some progress from our perspective, but here we go. Okay, without getting too much dragged down into the ethics rabbit hole, we have Randall, Lex, and then Katalin.
Great. Yeah, hi. Can you hear me?
Yes.
Yes. Okay, great. Thank you very much for both parts of your talk. I'm afraid I was about 10 minutes late, so I think I probably missed the most important bit at the very beginning that would explain to me the overarching problem being solved, which is what my question is about. Because when you explained how neuroscience of the hippocampus using auto and heteroassociative memory can be used to help interpret transformers, the part that was missing for me or that I didn't get was, is this meant to explain specifically why transformers give a particular result, or is it more of a general interpretation that makes an analogy between, say, the neuroscience system and the AI system?
So right now, I would say it's more the latter, but in mechanical terms, it's potentially possible for it to move into the former. So at the moment, people have noticed that there is a mechanistic kind of analogy that you can make, as I did in the talk, and that's not just something I found; it's other people. But cumulatively, if you add all those things up, then you can reinterpret transformers in this associative memory framework. And then something that I'm working on now, and I think others are also interested in, is to try to utilize that knowledge of associative memory and interpret transformers in that framework to help alleviate biases or other things. But exactly how to do that is not yet determined. So that's something I'm investigating currently.
Okay. So steps on the way there.
Yeah, right.
All right. Yeah. I have another question, but I think I'll let someone else go first and then I'll come back.
Okay.
Cool. Katalin, you go next.
All right, yes, thank you. Thank you, Thomas, for a very interesting talk and very nicely paced as well. Two different topics. Well done. I was also very excited. I just want to make just a general comment, and you're welcome to also reply that. I was very excited about this Top-Field Networks is All You Need paper when it came out. But it in my kind of information stream, it kind of got buried. It got drowned out by all the other crazy things happening. And I really lost track of, is this really a powerful tool? It looked very interesting. And I also didn't fully appreciate how the attention mechanism looks very weirdly close to what they're proposing. So maybe if you can comment just a little bit about, Is there progress being made? My more specific question was really about, I'm very interested in phenomenology and the relationship to basically population representation and activation in a sense. I'm trying to develop some theories around, how phenomenological experience arises from population activity. And you spoke a lot about degeneracy and redundancy. And maybe you can tell me a little bit about, might these kinds of approaches start to help us quantify, how many neurons do we need for something? That's the flavor I got. I didn't get this from talking to Jesse. I talked to Jesse before. I didn't get a sense that was something that, but I would be interested in this. Can you say a little bit more about quantifying degeneracy and redundancy? That's kind of my major question. We don't really have a guide for phenomenology. We're kind of like, nobody really knows. Does the quantum level matter for phenomenology? Does the circuits, which neurons talking about? So that's I'm a systems neuroscientist as well. Thank you.
Right. Yeah. As for the first question, yeah. So it seems to me that most people in the AI kind of space or neuroscience AI space, in wherever it interfaces, most people are more interested in developing further AI systems, right? More powerful ones. And so that sort of using these joint ideas to make new systems. There are fewer people who are trying to interpret transformers using associative memory as a framework, but I find it very promising. And yeah, and I encourage you to look at that paper again, or if you like, I have, I think, a pretty reasonable short summary in the appendix 1 of the paper that I mentioned. And as for the second point, it reminds me of a discussion I had earlier this year with Nelson Chia at Monash University, my original home university in Australia. And he's interested in using applied category theory to understand consciousness and phenomenology and so on, but from a neuroscience and psychological perspective. And I think that he, as well as his group, and I know one of the members of his group is actually also, I think, a fellow with you, right, Alison, right? So, and so we were talking about this, and I think that it's quite value laden, and I don't know, and it's not well formed, but I think that there should be common bases or redundancy in sort of some of these phenomena or some of these kind of structures which phenomena sort of latch onto. And you could say that those redundancies or common bases are due to some sort of objective reality in the universe, or you could say that they're due to some sort of societally constructed or biological motivations which ensemble these things together. So I'm not exactly sure. It's not my expertise, honestly, to comment further, but I think that there's certainly an interesting path to explore.
Okay. Yes. Thank you.
Yeah. All right. Well, feel free to ask a follow-up. I think in the absence of that, I'll go back to Randall if you want to go for your second question.
Sure. Yeah. Thank you. Yeah. My other question was if you could maybe explain a bit more about the problem of empirical risk.
Okay.
Maybe step it back a bit. If you could summarize empirical risk and then how using AI or transformers as something to look at neuroscience, how that helps deal with empirical risk. Mostly just because I know the presentation was great, but of course I'd like a kind of a sort of a top level summary where it's easier for me to just kind of hold on to it and go, these are the main points I have to remember.
I see. So the reason why we have to have empirical risk, it's because the expected risk, which is like a theoretical notion of how well the target function minimizes or aligns with the actual ground truth, that's unknown. So from the SLT perspective, these probability distributions are unknown, and so the empirical risk is just a proxy measure that we're using given a certain amount of data, and trying to minimize that function. And there are many ways to do that, right? You could use linear regression, you could use a transformer, you could use anything in between. But whatever process you use, you can then interpret using the idea that that's a learning process. And that learning process ultimately may not minimize to an individual function. It might have many different functions, and that's where degeneracy comes. So degeneracy is the idea that there are many different functions that could all do the same thing. And that set of functions that could all do the same sort of thing might be due to the fact that objectively this actual ground truth function does have many different solutions, or it could be having something to do with the empirical approximation, and it could be a problem of that. And so you might find that if you get more information, then this minimal set deteriorates or goes away in some sense. But generally, we don't find that. Generally, we find that both in neuroscience and AI, or machine learning, that there's ultimately many different solutions for the same function. Very, very rarely a function's completely unique. Yeah.
Sure. And then you tied that into, for example, the comparison of, say, place cells and grid cells, and how grid cells are used in making emerging place cells and all that. And, well, I mean, the grid cells, what they're mapping out is, say, at different scales, different patterns that you can use to then combine to identify a specific place, for instance. Mm-hmm. Or if it was human memory, then it wouldn't necessarily be place. It could be all kinds of concepts that you're mapping out in an episodic memory. So those are really components that you would use for every solution, right? Whereas the solutions would then be, say, taking this shortcut or taking that shortcut to get to a certain goal or something like that. So it's kind of, there's the components, and then there are the different solutions. Am I getting that right?
Yeah, I think so. And although I would push back a little bit on maybe the premise that place cells are absolutely determined by grid cells, or that grid cells are just sort of natural. I think that they're probably more, they're more warped and defined by like the environment and by what we
They do emerge instantaneously, though, right? Grid cells pretty much pop up instantaneously when you enter a new space.
Oh yeah. But how they develop over time and how they've been generated to develop in a genetic sense through evolution is, I think, a consequence of behaviorally wanting to do sequence prediction.
Right.
Yeah.
Right.
And and having the biases of space and time and conspecifics and different environmental niches and things like that.
Sure. Got it. Okay. Thank you.
No worries. Yeah.
Cool. Well, then I have a few questions, and feel free, anyone, to still raise your hand. I'm happy to take more questions, or just put it in the chat if you don't want to unmute. One of the questions I have is more about like the limits of kind of like the mutual benefit in which both of the neuroscience and the AI fields are benefiting each other. Like, do you think that there's specific problems where you just don't think that neuroscience, even though one would think that it may have an impact on AI and AI safety, you just haven't found that to pan out in reality, or the other way around of AI on neuroscience, where you're like, okay, just looking at AI systems, one would expect neuroscience, like the brain to behave in XYZ manners, but that's just not true. Do you know where that kind of like mutual beneficial relationship breaks down?
Yeah, I mean, I think it breaks down on a practical level in many cases because of like the systems just being very different and it being unknown how to map between them. And I think it also maps down on like a motivation level too. So, many AI people are more interested in sort of engineering type of questions, whereas many neuroscientists are more interested in like a natural science kind of question. So I think how to work past these, on the practical side is to build bridges that are explicit and helpful for both sides. I'm focusing on something that I know about, my little niche, and hope that it's going to be good. And as for the second part, I think, well, you can motivate AI people to care about neuroscience by saying, well, neuroscience might help us improve these systems, right? Once you've done the practical side of it. And on the neuroscience side, you say, well, these are like completely observable systems that we can have full control over, that we have potentially less ethical quandary over in terms of not having to kill animals for research purposes. And so we could help answer some natural science questions using AI systems or small neural networks. So I think you can fix both of these sides, the practical side and the motivation side, but it takes a lot of work and I can't do it alone. So I hope I have some allies.
Yeah, could you, I think in that spirit, share a little bit more about the work that you and your guys' team, the various ones, are hoping to take on perhaps in the next few months or maybe years? Is there any roadmap that you have in your head where others could contribute in useful parts? Or
Yeah, well, certainly if anyone feels that they know about transformers and have a strong idea how they work and or associative memory or memory systems and how they work, then I would be hugely interested to hear how you might think about, for example, the first part of the talk. And I think in general, there's a lot of low-hanging fruit around for people to, if they know quite intimately about one side of things, for example, the AI or the neuroscience, is to find some sort of partner on the opposite side of the aisle and to collaborate through that. And I think in general, mostly those collaborations don't form unless they're sort of facilitated by different groups. So, this community might be one that you could use to find someone that you can collaborate with. And in general, I suppose, anyone who's interested in these topics and bridging those gaps can contact me and I might be able to point in the right direction. In terms of my current roadmap, personally, I'm looking to develop associative memory theory or base theory of transformers. So right now it's quite focused on the attention mechanism, but as we know, there's many different parts of transformers and they contribute to different performance improvements or risks or opportunities. So those need to be sorted out and figured out. And it's quite possible that it may not be only associative memory that goes the whole way. It could be joining in with reinforcement learning or other sorts of topics, which also stem from neuroscience, it turns out. So I think that there's a lot to offer to that. And that's kind of probably the main project that I have in the next year is to develop a fairly good framework of like the neuroscience of transformers and large language models.
And like specifically, if your work in the next few years goes well, like in 3 years as an ambitious kind of target, do you think where could the field have advanced to there as like a carrot at the end of the road?
Sure.
If people really follow your lead.
Yeah. So, I mean, ideally we would have, so if everything goes according to my plan, I guess, then I would say there's a chance that we can identify these redundant bases, which form basically form the implicit sort of biases within large language models. And if we are able to do that, then we can understand how they combine and operate to perform negative things that we don't want, but also we can potentially steer them and identify ways that they can produce things that we do want. So I think that, in 3 years, if I had sufficient time and resources and so on, then I think a reasonable expectation could be that you could understand, I don't know, GPT-3, maybe GPT-2 using this model and understand the biases. Yeah.
Okay. Well, then we need to kind of like multiply those efforts so that we can get ready for GPT-5, etc.
Right. Exactly. Yeah.
Damn. Well, I mean, it's not unthinkable that once you can understand one of them, you learn like a few fundamental things that you could scale up faster to the next one. I don't know. Like,
right. Yeah, certainly. Yeah, this is premised on me working mostly on my own and with a few collaborators. But yeah, I think that hopefully if more people can join the efforts, then we can go quicker.
Cool. Well, then maybe my last question would be, how do people join? Or like, is there like anything that you guys have coming up immediately or any specific requests for collaborations that people should be aware of? I know that you had like, the final slides that outlined that a little bit, but like just having it at the end of the talk often helps.
Yeah. I suppose, just reach out personally to me if you want. But there's also, I think, some collaborators of mine who would be interested to hear from you if you're interested in these topics, like at Timaeus, a fairly new AI safety organization. But yeah, I think, if you just follow me on Twitter or something, you can contact me like that. Yeah.
Okay, I'm sharing your Twitter handle again also here in the group. Then it's perhaps a little easier. And maybe last question, since we still have 2 minutes, could you share a little bit more about Timaeus as well for those that may not know? Like, I think it's like really pretty freshly baked. And
Yeah, so it's a great new organization, and they're working heavily in statistical learning theory. I think they were quite pleased to have someone like myself with a non-physics background coming in because, they were mostly thinking about it from some physics angle and mathematical angle. And so bringing some developmental biology or neuroscience experience to that, I think was quite helpful, but they're quite interested in that. So if you're interested in these topics, you should check them out. And yeah, that they are doing some really heavy stuff. But you don't need to know like algebraic geometry or something to help with them. You can just check out. I think they have a list actually on their website. If you're looking for like practical open problems and you're like more engineering focused, I'm pretty sure they have on their website a list of like kind of open problems or problems to tackle in their framework.
Great. All right. Well, we'll try to at least send everything with a follow-up and include it in your seminar summary. But hey, I thank you so much for joining us. That was really, really exciting. I think you're just getting started and there's already so many parallels and bridges to be built. So thank you so very much. Thanks everyone for your amazing questions. And I look forward to seeing many of you here again for the next one. Thanks a lot. Have a wonderful rest of your day.